Okay, so welcome everybody to this online seminar on complex analysis and allied topics. And it's a great pleasure for us to have today Daniel Girela from Universidad de Malaga in Spain, who's going to talk about superposition operators acting on spaces of analytic functions.
Okay. So let me start thanking Marco, Filippo, Nicola for organizing this nice seminar. Actually, in this situation that we have that we cannot travel, and so it's very nice having the opportunity of listening to so many nice talks that you have included in the seminar, and of course for the invitation to participate in it. So I'm going to speak about superposition operators on analytic function spaces. This is something I have been working for several years, and I'm going to introduce some of the ideas that we have used working in this topic. So let me start introducing the notation. Of course, the usual notation, we will denote the unit disk in the complex plane by D. And all of this is going to be the space of all analytic function in D. You are all very familiar with composition operators. If you have an analytic function in the disk, we map the disk into itself, then the composition operator C phi is defined by composition. You take any function, then any function in the space analytic in D, then C phi of F is just the composition of phi with F. And this is there is a huge literature on composition operators. And of course, you know a lot about it. And of course, this is a linear operator. But we are not going to speak about composition operators. We are going to speak about superposition operators. Superposition operators in some way is similar, but the composition is in the other way. So what we have is an entire function phi, and then we consider the superposition operator from analytic function in D into analytic function in D is defined in this way. If we have an analytic function in D, so S phi of F is F composed with phi. So it's composition, but in the other way. And of course, the natural question that we have in this setting, similar as the one that we have in the setting of composition operator, is the following. We have two natural spaces for analytic function in this, say, Banach spaces or Frechet spaces, something like this. And we want to characterize the functions phi so that S phi maps X into Y, and we can speak about continuously bounded or something like that. So this is the natural question. Let me see. There is a remark that I have to do, which I said before that composition operators are of course linear operators, but in general, the superposition operator is not linear. In fact, it is very easy to see that the superposition operator with symbol phi is linear if and only phi is a multiplication by a constant. So this represents some big difference with composition operator, and in particular, since this operator is not linear, assuming that we are working here with linear spaces, say that the space X and Y that we are going to consider essentially are Banach spaces for analytic function or Frechet spaces, then in general, since this S phi is not linear, continuous and bounded may not be the same. So this is something that I have to remark. So to start with, we don't know that a continuous operator from S to Y is the same as we bounded, as happens if the operator would be linear. But as I said, it's not linear, so this may not happen. And this is one big difference with composition operators. Okay, let me say something very trivial. If the second space Y contains all the constant, and we take as phi a constant, is trivial, that says phi maps X into Y. Also, if we take as phi the identity mapping, then of course we have that S phi of f is equal to f for every analytic function in D. So if we taking as phi the identity mapping, we have that S phi of x is included in Y is the same as saying that the space X is contained in Y. So having this in mind, then we can say in some informal way that when we have the two spaces that we are working with, X is contained in Y, say the answer to our question, that is characterizing the functions, the entire functions phi, so that S phi of X is included in Y, in some way tell us how small is X compared to Y. We can say that if there are a lot of entire function for which this is true, this gives an idea that X is quite small compared with Y. Let me introduce a notation. When this happens, when S phi of X is included Y, we usually say that phi acts from X into Y by superposition. So in some, probably in some transparencies ahead, I will use this notation. When S phi of X is inside Y, usually we say that phi acts from X into Y by superposition. So let me see. This is more or less so the question is this that we want to consider is this: we have two spaces of analytic function, and we want to characterize. And what happens is that this has been done for a number of pair of spaces, and actually there are some quite different ideas in having used for different spaces. And then what I want to do is try to explain some of these different ideas that have been used to consider this in some of these cases. More or less, the result that I'm going to speak about having obtained in some works that I have done in the last few years in collaboration with Ausi Marquez from Malaga, Petros Galanopoulos from Thessaloniki, and Salvador Dominguez from Malaga. This is a Ausi and Salva are former student of mine, and Petros is a collaborator from Thessaloniki in Greece. So let me see. Let me start saying a little bit about the result that we knew when we started to think on these kind of topics. And of course, the spaces that we are going to consider are going to be the classical one. So the spaces that we are to consider are the very well known to everybody. So we're going to work with Hardy spaces. I guess I don't have to say what the Hardy space is. Hardy space HP is the set of analytic functions in the disk, so that the integral means of order P are bounded. And so this is the user notation. We are going to work also with Bergman spaces and Dirichlet space. If we have P bigger than 0 and alpha bigger than -1, the Bergman space AP alpha is a set of analytic functions in the disk which are in LP of the disk with respect to this way, the weight 1 minus mod C squared to the alpha dAc, where this is the area measure in the disk. When alpha equals 0, we simply denote this by AP. So these are the usual weighted Bergman space, the standard weighted Bergman spaces we are going to consider. And the Dirichlet space, dP alpha are the set of analytic functions in the disk, so that the derivative is in AP alpha. So these are more or less the classical space we are going to consider. And I'm going to speak also about two of my favorite spaces, which are the Bloch space and BMO. The space BMO, you know, is the space of all analytic functions in the disk whose boundary values are in BMO of the boundary, so that they have bounded mean oscillation. And you all know that BMOA can be characterized as the as the dual of H. And the Bloch space is the set of all functions, analytic in the disk, so that the supremum of 1 minus mod c squared f prime of c is fine. And there are some relation well known between this space and Hardy space, which is, of course, BMO is containing the Bloch space. H infinity is some space BMO is in between H infinity or all H P space, but there is no relation between, of course, H infinity is included in Bloch, but there is no relation between Bloch and the intersection of HP space. Well, I'm not going to say anything. These are the more classical space, and I guess that you all know very well all of them. So I'm not, but these more or less are the space I'm going to work with. And then, as I said, I'm going to start recording some of the results that were known before we started to work in this question. And in fact, the first result that I know are the action of superposition operator between Hardy spaces and between Bergman spaces. And then Cameron and Jimenez, they studied this, and they proved that the superposition operator is phi maps HP into HQ or AP into AQ if and only if it's a polynomial. Then I guess that the next quite important work in this topic was one by Buckley, Fernandez, José Fernandez, and Dragan Vukotic, that they studied superposition operator between certain D-less type spaces, the spaces DP0 and DQ0, say. And let me introduce another result that was obtained by Nacho Alvarez, Ausi Marquez, and Dragan Vukotic, that they study superposition operator between the Bloch space and Bergman space. And they proved this result. I'm going to state one of the results that is the following. The superposition operator S phi maps AP into the Bloch space if and only if it is constant. And if we go in the other way, S phi maps the Bloch space into the Bergman space AP if and only, well, the condition that they obtain is phi is an entire function of order less than 1 or of order 1 and type 0. Well, if you see that this result, the condition that we have over here, we all know that the order and type of an entire function is preserved under when we differentiate. If a function has an order, the derivative has the same order, and the same happens with type. And actually, so in the result that they have proved in this here, then we can say that if phi maps AP into B, then S phi prime also maps AP into B, and also here is if S phi maps the Bloch space into AP, then so does S phi prime. And of course, the results that are obtained here also has this property, and the result that they obtain here also. And in fact, all the results that I know have in common this property. All the result that I have mentioned before, and actually all the results that I know have this in common. That if we have two spaces, X and Y, and phi X by superposition from S to Y, so does F prime. But this is what is true for all the examples that I know. Then I think that I gave a talk on superposition operator, I don't know, 3 or 4 years ago, I don't know exactly, I think it was in Portugal. And when I finished the talk, there was some question, and one question was by Eva Gallardo was the one who asked. She asked, is this always true? Is that if S phi maps X into Y, then F prime also? So I said, all the examples, my answer was all the examples that I know are of this kind, but actually I cannot say the. So this is the question that after this meeting on this question, then I started thinking, and I had a student who was working on the PhD thesis, and then we started working with him in this question. So the first question is this always true? Or maybe this is something that we haven't been able to prove, but then we decided at least try to prove some results like this. Try to find a general theorem in this line. A general theorem in this line is, let's see if we can find some classes. Actually, what we have done is we have found some classes of spaces Y which has the property that if phi is an entire function, so that S phi maps X into Y, then the same happens with S phi prime. This is the result that we have obtained. And let me explain what are these classes of spaces. So here I have to introduce a new class of space, which are also natural, but are not the one that I mentioned before. These spaces are a space of restricted group. So we are going to consider a weight in D, and we are going to say a weight is going to be simply a positive and continuous function, and we are going to say that this is radial. And we are going to ask that V is strictly decreasing in 0. And then we consider the spaces H infinity V are the space F, so that the supremum of V of Z times the absolute value of F of C is fine. These spaces have been extensively studied, for instance, by Bonnet, Lasky, and so on. And then what we have done is that we have proved, and in fact, well, let's see, I think also Bonetti and Bukotic studied superposition operators acting between one space of the type H infinity V1 and another space of the type H infinity V2. But now what we have proved is that if we consider the question that I mentioned in my previous transparency, then this result, we can take Y as this space H infinity V, so that this property is true. So actually what we have proved is the following. That if we have any weight as defined before, and we have an entire and a space X, any space X of analytic function in the list, a Banach space, actually what we have, if we have an entire function so that S phi maps X into H infinity V, then so that S the superposition operator induced by the derivative of phi. So more or less what is, I'm going to say a couple of ideas that we have in the proof. Well, the first part is completely trivial. Suppose that S phi maps X into Y as a bounded operator. Then we start, this is quite easy. Then we obtain a bound for phi prime of f of c when f of c is small. This is just a simple calculation. But the important thing is that we need some other estimation when f is big. And when f is big, what we are able to prove is that if we take a function f in x and we take a point where f is big, then we can obtain a bound like this, that we cannot find a function g in x, which this function g actually depends on z, so that and with the same norm of s, so that this inequality is true. And then once that we have these two steps, then it's not difficult to prove that actually the S phi prime of f is in H infinity. So we have at least we have obtained a class of spaces Y, so that the answer to our question is true. But well, this space H infinity V are natural, but I guess are not the most popular spaces in there. But a more popular space, of course, is the Bloch space. And what happened is that actually we can obtain a theorem like this if we substitute the space H infinity of V by this, the space that I'm going to call in this way, the function, the analytic function in the D, so that F prime is H infinity of V. So we have the same theory, but taking this space as Y in the previous one. So the theorem is the same. Suppose that we have a weight, an X a Banach space of analytic functions in D, and an entire function. And then we can prove in a similar way to what we did before, that is the superposition operator S phi is a boundary operator from X into this space, then the superposition operator induced by phi prime also maps X into this space. And of course, what happens if we take this weight? If we take this weight, the space D H infinity V is simply the Bloch space. So we are right to one of my favorite spaces. So I are right to the Bloch space, and so as a particular case of the previous one, what we have is this, that the Bloch space is one of those Y's that we can take to answer to the question that I raised in the beginning. So we have that if we have a Banach space of analytic function in D and an entire function, so that S phi maps X into the Bloch space, then so does the S phi prime. So, but anyway, but the question, but this is what we have been able to prove. In fact, last year I was trying to prove whether this was true for BMO instead of the Bloch space, BMOA, and so far I haven't been able to prove it. And so actually, this is, as a general theorem, this is what we have been able to prove. We have not been able to prove for other spaces, as the BMO. For instance, I guess that it has to be true. If we put BMO, we put, instead of the Bloch space here, Hardy spaces also, but we haven't been able to prove it so far. So this is the first question but now the other thing that I want to speak here now is that, as I told you, we have found several different ideas to prove results on superposition operator. And then I'm going to try to explain a couple of those ideas. The first one is that we can use information on the set of zeros of an analytic function space as a tool to study the action of superposition operator on those spaces. And let's go back to one of the results that I mentioned before. One of the results that I mentioned before was obtained by Nancho, Alvarez, Marquez, and Bucotti, was the following. And this is an example of the result that I mentioned before, that if we have an entire function so that the superposition operator S phi maps the Bergman space AP into the Bloch space, then phi must be constant. The original proof that they gave of this result used result of conformal mapping and so on. But we have been able to prove actually an extension of the result because we can take weighted Bergman space, but using several ideas different to this. Actually, we have been able to extend this considering actually weighted Bergman space, and the result is the same. Suppose that we have an entire function so that S5 of the weighted Bergman space AP alpha is inside the Bloch space, then phi is constant. And the way that we have proved this is using information about the sequences of zeros of this space. Well, we know a lot about this, the sequences of zeros of function in the Bergman space and in the Bloch space, and these are the ingredients. The basic idea is that there is a zero sequence of the space AP alpha, which is not a zero sequence of the space Bloch. And actually, If we have actually the result that we are going to use, I guess, are pretty well known, that if we have a Bloch function which is not identically zero, say that f of 0 is not equal to 0 and ck is the sequence of zeros of the function f, then we can take this product from 1 to n of 1 over mod ck. This is big O of log n to the 1/2. This is something I don't know exactly, but this is something that I proved in collaboration with Maria Novak and Piotr Braniewski 20 years ago or so. And of course, you all know all the work of Horowitz on the zeros of Bergman spaces. And among other things, they proved that if we have the sequences of zero function in Bergman space, if we consider this kind of product, the growth of this is something potential. This is a logarithmic growth, and actually it's potential. There are some cases where this is actually of this kind. We cannot put here for a certain function, we cannot put here anything of the kind of logarithmic way. So in this way, we have what I said before is quite clear. There is a function, there is a function in the Bergman space AP alpha whose sequence of zeros cannot be the sequence of zero of any Bloch function. And so this is actually the ingredient that we need to use this to prove this theorem, because what we do is the following. Suppose that we have a function, an entire function which is not constant, and S phi of AP alpha is inside V. Then I take the function in AP alpha that I mentioned before, a non-identically zero whose sequence of zeros is not the sequence of zero of any function in the Bloch space. And then we take since we are assuming that this, then S phi of G is a Bloch function and is not constant. And then we consider this function and we subtract f of 0, and then we get here a function which is in B, and all the zeros of G are zeros of f. But this is impossible because that sequence could not be the sequence of 0 of a function in Bloch. So this is the idea that. So this is one example. Actually, we have been able to, we have used these ideas in some other space, and maybe later on we are going to introduce such a result. But actually, the idea that I have explained in that example can be generalized, and in general we can state some result like this. Suppose that we have two space of analytic function in the disk. We need some condition that there is some function in X, which is not identical to 0, whose sequence of zeros actually essentially is not the sequence of zeros of a function in Y. And then if we have an entire function which acts by superposition from X into Y, then phi has to be constant. And then we can use this in a number of cases. But I'm not going to get more into this. I have more or less explained a little bit this idea. But now let me go to some other question. I'm going to speak a little bit about Hardy space and dpp-1 spaces. I'm going to consider this space because these are, I guess, my favorites among all dp alpha space. Because among all the dp alpha spaces, the space dpp-1 are the closest one to the Hardy space. We have this inclusion, dpp-1. Actually, for p equal to d to 1 is exactly the Hardy space. But in general, if p is less than 2, dpp-1 is a subset of HP. But if we go for p bigger than 2, the inclusion goes in the other way. And I introduce here the Bergman space A to P, but actually, let's think a little bit on this. So in some cases, these spaces, these spaces are very close to Hardy spaces. There has been a lot of work over the years studying similarities and difference between Hardy spaces and the corresponding dp-1 space. And I'm going just to mention a little bit of similarities and a little bit some difference. About similarity, for instance, we can say that when p is less than 2, the Carlson measure for HP and the Carlson measure for dpp-1 are the same. For instance, the univalent function in HP spaces and the univalent function in dpp-1, these are the same, but this is for all p. And actually, over the year, it has been proved that a number of operators are bounded on HP if and only if they are bounded on dpp-1. These are some similarities, and let's speak a little bit about differences. Well, H infinity, of course, H infinity is included in all HP spaces, and but the H infinity is not included in the space dpp-1 when P is smaller than 2. There are functions here which are not bound. In fact, there are even Blaschke products which are not in any of the dpp-1 space. These are different for P smaller than 2. If we go for P bigger than 2, in dpp-1, there are functions without radial limits. And we know that in Hardy space, all functions in Hardy space have radial limits almost everywhere. There are no inclusion between this space. If we have P not equal to Q, we cannot say that neither this is included in this, neither this is included in and we know that for Hardy space, of course, we have inclusion. If Q is bigger than P, as Q is included. The zero sequence of function in dpp-1 for P bigger than 2 may not satisfy the Blaschke condition. Of course, we know that the zero sequences of Hardy space, they all satisfy the Blaschke condition. And I said before that when P was less than 2, the Carlson measure for dpp-1 and for HP are the same, but this is not true if P is bigger than 2. So there are similarities and differences. Then we decided to work a little bit on see whether superposition operator can tell us whether there are differences or similarities in this space regarding superposition operator. So studying similarities and difference between the space HP and the space dpp-1, but regarding superposition operator. And then what we did is trying to consider the Bloch space and BMO space, trying to consider what are the superposition operators from the Bloch space into Hardy space or into dpp-1 space and see whether we obtain the same result or different. So this is what we are going to. I'm going to speak a little bit about this. So we want to see whether this superposition operator between Hardy space and the space BMO or Hardy space into the Bloch space are the same, are the corresponding between dpp-1 and BMO on dpp-1 in the Bloch space. So let's start thinking a little bit. Actually, the first result that we obtained, this is actually something that we obtained, I guess it was like 10 years ago. Actually, we work on this superposition operator from the Bloch space into HP. Then we can prove this. But actually, this is something that can be proved using the ideas of the sequences of zero that I mentioned before, because there are Bloch functions whose sequences of zero do not satisfy the Blaschke condition, and all the function in HP satisfy that the zero sequence satisfy the Blaschke condition. So this result can be proved also using the ideas that I mentioned before about zero sequences. So this result, this is something that we proved, but I mentioned that actually this can be proved using these ideas of that. But for BMO, about BMO, this is something that we prove. What we prove is different. So here, of course, we between BMO and HP, we cannot use the idea of the sequences of zero because the sequences of zeros of BMO are the Blaschke sequences, and the sequences of zero of HP are the Blaschke sequences. So we don't have that tool in this setting. And what happened is that actually the superposition operator between BMO and HP are not they do not reduce to constant function. The result that we obtain is that an entire function acts by superposition from BMO into HP if and only if finds an entire function of order 1 type 0, or order less than 1 or order 1 at type 0. I'm not going to give the details of this proof, but actually I guess that the basic ingredient here is the John Nirenberg theory. I should mention that actually this result, we proved this result not only for BMO and for the Bloch space, but we consider the QP space. Some of you are familiar. QP space are some family of subspace of BMO when Q is smaller than 1, and we obtained that this result here remains true if we put here any QP space. But I'm not going to get into that, and in fact I'm not going to give details of this. I mentioned that the basic step to prove this result is the John Nirenberg theory. But we have this. But then once that we have this, then the question that we decided to think about several years later was, what happens if here we don't put HP, if we put dp p minus 1? To see whether we obtain some similarity or some difference between HP and dpp minus. So this was the idea that, and then we and then in a word that we did with Ausimarke and with Petro Galanopoulos, then we work on this, on the superposition operator from the Bloch space into dpp minus 1 and from BMO into this. And then let's see what happens. Let me see, there are some things which are easy to say. This is the result that I have just mentioned, that S5 applies the Bloch space into HP if and only if P is constant. So if we take P smaller than 2, since dp p minus 1 is included in HP, then from this we certainly obtain that the result is the same if we put here dp minus 1 and we restrict to the range 0 less than p less than 2. So for p less than 2, the result is the same. We obtain the same result if we put here HP or dpp minus 1. But what happens if we consider now the case p bigger than 2? P bigger than 2. So what happens is that when we put p bigger than 2 and we put here the Bloch space, we are going to obtain also the same result. But in this case, actually, the ideas are going to be different, and the ideas go also. This can be proved also using the idea on the zero set, because it's the same. The zero set of a Bloch function, as I mentioned before, satisfies this condition, and the zero set. And actually, this is shared. This is what I mentioned before, but actually. Maria Novak proved that this big O cannot be changed to little o. So there is a Bloch function so that the product of 1 over absolute value of an is not little o or log n to the 1/2, where an is the sequence of zeros of p. This was proved by, I guess, it was proved even for, not only for Bloch function, I think she proved this for a normal function, but anyway, so that the result is shared in this way. But what happens when we take function in dpp minus 1. When we have function in dpp minus 1 and p is bigger than 2, we can obtain this sharp result. And then comparing the set of function in the Bloch space and this condition, and we use the idea that I mentioned before, then we obtain that a superposition operator from maps the Bloch space into dpp minus 1, in this case, if and only if it's constant. So what happens is that when we consider the superposition operator from the Bloch space into Hardy space, are exactly the same as the superposition operators from the Bloch space into the space dpp minus, and they are constant. So if we take the Bloch space, then we find no difference regarding this kind of superposition operator between Hardy space and dpp minus 1 space. But what happens now?
Daniel, may I ask you one thing?
Sure.
So that condition you wrote in the previous slide on the zero set of functions in dpp minus 1, I imagine that this condition does not characterize the zero set.
No, it does not characterize. This is a condition like of the type of Horowitz for Bergman spaces, but
okay, so it's just a necessary condition.
Yeah.
Okay, thank you.
Okay. Now then let's go to BMO. So now we are going to try to see what happens the superposition operator from BMO into dpp minus. Let me see. The result that I mentioned before that we have obtained for BMO and HP was this, that the superposition operator S5 maps BMO into HP if and only phi is of order less than 1 or of order 1 and type 0. The same result and usually the same technique exactly gives us the same result if we put here instead of the Hardy space the Bergman space. So if we have a superposition operator from BMO into AP, this is equivalent to saying that phi is of this order and this type. And then what happens? So using this result, then we can prove in the case 2 less than p less than infinity, HP is included in dpp minus 1 and included in A2p. And then we use these two results, and then we obtain that in this setting, we obtain the same result. That when p is bigger than 2, a superposition operator maps BMO into HP is the same as that it maps BMO into A2P, and since this space is in between, because it's the same that it maps BMO into dpp minus. So for p bigger than 2, we don't have difference between HP and dpp minus 1 in this setting, just as before. But what happens now if p is smaller than 2? Well, in this case, then we have that for p less than 2, the superposition operator which apply BMO into dpp minus 1 are not the same as those which apply BMO into HP. Because actually the result that we prove is the following. For BMO, as I mentioned before, this was saying that phi is of order 1, order less than 1 or order 1 and type 0. But if we take here dpp minus 1, the result is this, that the superposition operator S5 maps BMO into dpp minus 1 for this range of p's if and only if phi is constant. And let's see, here we are going to use a different idea to prove this. So suppose that we have suppose that we have a function phi, an entire function which is not constant, and maps and the superposition operator S5 maps BMO into dpp minus. Then let's see. We're having p less than 2. If p is less than 2, then h infinity is not included in dpp minus 1. So this means that there is a function f in h infinity which is not here. which is not here. This means that the integral of 1 minus mod z to the p minus 1 times f prime of z to the power p is infinity. But actually, this is a result stronger. We can prove that actually this there exists a function so that the integral that we obtain along all these radius is infinity for almost every z. That this is a result that actually I think I proved this long time ago. I don't know the year that it was. 25 years ago or so. Then actually is it possible to prove the existence of a function in H infinity which satisfies that this integral is infinity for almost everything. We are having p smaller than. But the construction can be used first working with Hadamard series. If we start with Hadamard series, then we can prove that it's a function in H2. And then we do something, we work with that function in H2, and then we are able to obtain a function in H infinity satisfying this condition. But anyway, this is something that was proved long time ago. But then using this, we can prove this. See, suppose that phi is not constant, and we take this function. Phi is not constant, then it's the same as saying that phi prime is not identical to 0, of course. And then if we consider phi prime f composed with phi prime, this is of course in H infinity because f is in H infinity and the function is not identically 0. Since this is a function which is in H infinity, then it has a radial limit almost everywhere. By using the Riesz uniqueness theorem, this radial limit is non-zero almost everywhere. So this function has a non-zero finite radial limit almost everywhere. And then it's just working a little bit on the condition. We are assuming that S phi of f is here. We write what this means. What this means is this. And then we write this in polar coordinates. This is saying this. By saying this implies if this is finite, this means that for almost every theta, this integral has to be finite. But recall that I said that f prime composed with f has non-zero radial limit almost everywhere. And then using this here, then this is easy to prove that this implies this, and then we get a contradiction, more or less. Once that we have the idea, then these are just writing things and one get contradiction. And so I guess this. So I guess this is all I wanted to know. Well, these are the articles that were these things. As I said, this is a old paper. This was the one that we studied the superposition of operator from BMO and hard space. Actually, we consider QP space. And this is the one that we consider the superposition operator from DPP, from the Bloch space and BMO into the space DPP-. And these are the more recent work that we have done with Salva. And there is some result that I cannot mention, but we have obtained also with Salvador Dominguez, result on the superposition operator acting on Bezo space and on mixed norm space. And so I guess this is all. Thank you very much. And let's see.
Thank you very much. It's very interesting talks. So are there questions?
I have a question which is maybe rather marginal. You cited the problem of characterizing the Carlson measures for these dp p-1 spaces. Mm-hmm. Is there any new thing?
No, I don't. Actually, I haven't worked on this since in the last 3 or 4 years. I haven't thought, but actually, I don't know anything new in the last few years.
So you had this surprising result.
Yeah, that this not for P bigger than 2. This was surprising, yeah. But characterizing in some natural way what those Carlson measure. I don't know of any progress in the last few years.
Okay, thank you.
I don't know. There is a paper by Falla or something like that that they say that I have read, but I haven't read in detail. They say the title of the paper is a Box condition for Carlson measure on the Dirichlet space. So maybe this can, but I don't know. But I guess it's not a characterization. But maybe in that paper there can be some idea which can be used for this. But actually, I don't know.
Okay, can you send me the
Okay, I will try to find it and I will send you the.
Okay, thank you.
Other questions?
I have a question.
Marco?
Yes, thank you for the talk. But I have maybe I missed something at the beginning, or maybe my question is very stupid. But you consider spaces somewhat. So the spaces are very different from each other. HP or BMO or Bloch.
Well, maybe they are not so different from each other. For instance, if we take this HP and DPP-1, they are very, very close, as at the end. Some of them are very, very far one. For instance, the Bloch space and the Hardy space, in some way, they are far from each other in some way. But for instance, the last space that I have considered DP-1 and Hardy space, they are very, very close. So,
okay. What about besides the identity to Y? So if you go from H itself,
I don't know. I'm not hearing you. Really.
What if you take functions that are superposition from HP to itself, say?
From HP to itself, well, this is the result that the first result that from HP into SQ. This is very easy actually to obtain because it's a polynomial. You just have to use the growth of the function in Hardy space, and then the polynomial growth that you need to go from one to the other one is the result that you get.
And this is a general thing about so even if you change space not from HP but from a Bloch or BMO, you still get the same polynomial. Okay.
No, if we go from Bloch or BMO, no, we don't get polynomial. Because more or less, if you just look at the growth of function in Bloch on BMO, they have logarithmic growth. And Hardy space, they have potential growth. So you have something different for sure. But if you go from Hardy into Hardy or from Bergman into Bergman, you have more or less growth of the same kind. And then this is the difference.
Okay.
Okay.
Yes. Thank you.
Other questions? Okay, so Daniel, maybe I have just, it probably is a very naive question. So composition operators, you get information, of course, they are linear, they're not, but you get the information according to the dynamics of the symbol.
Sure.
Like, I mean, compactness, cyclicity, hypercyclicity, and so on. So here, is there any results which is based on the dynamics of the symbol?
Actually, I don't know of any result in this line. Actually, no. Really not. We have some people use result in conformal mappings, and they even use, for instance, drag and Bukotic and so on. They use some result on the pseudo hyperbolic method and things like that. But on dynamics, I don't think any work using anything having to do with the dynamics really.
Do you think it's something that?
Well,
sense,
the thing is not linear, so I don't know exactly, but it might be. I don't know. Maybe it might be, but really, I don't know. But the thing that is not linear, maybe I'm not sure.
Yeah. Thank you. So, other question, comments? Okay. So if not, we thank Daniel again.
Well, thanks to you.